Hi, and welcome back. This is Dr. Dan here, and what we're going to be looking at is stoichiometry. So, stoichiometry is one of those really big concepts that we go over in general chemistry, and this can be one of the scarier concepts that you can go across. So, we're going to go over exactly what this is about and what you need to know. So, when it comes to stoichiometry, the whole idea is that these are chemical calculations to measure the amount of reactants and products in a chemical reaction. So what we're going to be trying to do is putting chemical reactions to work, which is all going to answer a bunch of different questions. So when we're looking at those questions, we want to know how much are we going to make of a different product when we are mixing these different vessels together? How much reactant will I need to make this reaction happen? It helps save a lot of time for chemists. It gives you that ability to be able to predict things, which is crucial when we are looking at individual chemical reactions. We want to be able to predict. So that's one of the things we're going to be looking into in this video as we start to move forward. And I'm going to go through a bunch of easy tips to be able to see exactly how we can go through stoichiometric equations. So as we go through these different videos, what exactly is our goal? Well, and the goal is always the mole. What we are always trying to do is convert from one unit to another. So when we go through these, we are always trying to convert from, let's say, from moles to moles or from grams to grams. We're trying to do simple ratios. So like we said, we're putting chemical reactions to work. So stoichiometry, it starts at the balanced chemical reaction, meaning that if I take a simple reaction, let's say if we have zinc in HCl, when these reactants are coming together, if I put zinc in hydrochloric acid, well, what is going to happen? Well, we're going to see a single replacement reaction, meaning that we're going to be taking that zinc atom and it's going to be replacing the hydrogen in the HCl. So when that occurs, we're going to be creating zinc chloride and H2 gas, which if you remember, why H2, this is one of our diatomics. So it's one of those 7 diatomics that we always see all the time. So single replacement, they follow that A plus BC leads AD plus B formula. So that's our little recipe we are going to follow to help predict this reaction. And then what we're going to do is make sure we swap drop it and then balance it, which if you need help with trying to balance chemical reactions, look at my previous video on types of chemical reactions and how to balance chemical reactions. So the big thing is here, what does this formula tell us? There is a story that is hidden inside of the coefficients. The coefficients reveal exactly what it is that is inside of this particular formula. It gives us a preview of really what to expect here, which is always very, very powerful for us. So let's take a look at it. What exactly is it that we are seeing? Well, if we look directly at these coefficients, we can see that 1 mole of zinc, when it's put in this reaction, it needs to react with 2 moles of HCl for a complete reaction. We can also see that 1 mole of zinc will create 1 mole of zinc chloride, or that 1 mole of zinc will create 1 mole of hydrogen gas. It tells a story of how much is needed and how much you are going to create. So how many atoms or how much mass goes in and how much mass comes out. Now, it's not the only thing. You can tell this also from HCl as well, or any of the species. You can say 2 moles of HCl is equivalent to 1 mole of zinc chloride made, or that 2 moles of HCl is equivalent to 1 mole of hydrogen gas actually shown. So these coefficients, they represent mole to mole conversions, which is one of the most important things that you need to know for stoichiometry. So with that being said, how can we do these? So this is a how-to guide. So the first thing that you need to do is balance that chemical equation. Next, what you're going to have to do, the second step, is use that mole to mole ratio to represent the species that are in it. But you need to have a balance in order to do that. So make sure you're practicing how to balance. So, but the thing is, like, do you measure moles in lab? And the quick answer is no. We don't have a moleometer to be able to measure that. That's not something we do measure, but we do measure mass. We can go from mass, we can start off our experiment, we can go to our little balance, measure the mass of one thing. We can use molar mass to convert that to moles, which we can then do our mole to mole ratio to then get to a new product and then convert it to mass again. So with all this being said, we have a bridge between all these different species. We can go from mass of A, or our reactants in this case, to moles of our reactants, A, that I have labeled here. Or when we go through this, we can also, then we can convert that to our mole to mole conversion, whether it be reactants or products, like how we just looked at with our zinc reaction. And that can be converted then to mass. It is a bridge. Stoichiometry puts our equation to work to help us be able to balance things. Now, so our previous equation, we have to add a step here. So being that we start with mass versus moles, we have to add that in as number 2 here and move our mole to mole ratio down. So our step-to-step guide is we need to balance the chemical equation, start with mass of A, convert it using molar mass, and then we are going to use the mole to mole ratio to convert to other species that we are interested in trying to represent. Are we trying to figure out how much product are we making? How much of whatever this individual reactant is? It's all about putting the pieces together. Then our last and fourth step is converting moles of our product to grams, or the mass of, to using molar mass again. So it's 4 steps to do all these stoichiometric problems. So I'd recommend writing this down. You will need this for chemistry to help pass chemistry. So let's take a look at this. Let's do an example. So if I have the following problem where I have butane gas, it's a hydrocarbon, and it's undergoing combustion to produce carbon dioxide and water. So let's go through our steps. The first step is that we have to balance the chemical equation. So if you remember from types of chemical equations, there's 5 major general chemistry reactions. One of them was combustion, meaning that a hydrocarbon is always reacting with oxygen to create water and CO2. So let's do it. So we'll write out first all the individual elements for each species. We will count everything on all sides. And one of the little things is when it comes to trying to balance these equations, when we see that we have multiple oxygen sources on the right-hand side of the equation, right? We have oxygen coming from water and from CO2. This can be a little tricky in order to balance, right? As a total, it has 3 total moles of oxygen on the right-hand side of the products. This is we have to first try to even out the oxygens. So if we do that, one of the things that we are looking at here is, can we easily do that? So if I start with trying to put, let's say a 5 in front of the hydrogens, meaning right now I'm looking at the hydrogens on both sides of the equation. We have 10 on the left, and right now we have 10 on the right. If I do that though, one thing you will see is that the oxygens will still remain odd overall. We'll have 5 oxygens from water, 2 from CO2, which is not going to ever even out, especially when we have 4 carbons on the left. So it's one of those tricks that if you see that this is odd, try to first double the amount of butane that we have, or whatever your hydrocarbon is, in the reaction. So if we double the amount of butane, one thing it's going to do is help us even out all of our individual coefficients that we have here. So when we balance out our hydrogens, we then have an even number of oxygens, which then allows us to quickly balance the entire equation, right? And if worse comes to worse, if you have too many of something, let's say if you can divide everything by 2 or by 3, you can always simplify the equation in the end by doing that little multiply by 2 trick. And then the last thing we always do is we save oxygen for last. So going through this, our next step is now that we have a balanced equation, we need to convert mass of our reactants to moles. Now, in the original equation, I forgot to write down how much mass there was, but one thing that we are given in this problem is that we have 236.5 grams of butane that is being used. And we want to know is how much CO2 will be generated. So if I'm going to be burning a flame, I want to know how much gas am I going to be creating that it could be potentially breathing in or creating within this reaction. So when it comes to industry or pharmaceutical industry, we want to try to figure out how much are we going to be creating. We want to know, we want to maximize our profits or reduce our danger risks that are in a equation. So when we do this, we are going to be setting up our T table to try to show this conversion. So if you remember, first we go from mass, then we do molar mass of butane. So we add up all 4 carbons, the 10 hydrogens in this. And then as we go through it, we'll see that the molar mass is 58.12 grams of butane. And that's equivalent to 1 mole of butane. So when we set this up, we can cancel out our grams, which will then allow us to acquire moles. Now, is this the final expression? Well, we want to get to grams. So step 3 is the mole to mole expression. So the beauty of stoichiometry is you can set this up to be one big calculation, just like dimensional analysis from when you first started general chemistry. So if you take those moles, you're going to then look at your chemical equation, which tells that coefficient story of if I have 2 moles of butane that's going to be used, it's going to create 8 moles of CO2 as a result. So, and that's the wonder about it. So this allows you to be like an alchemist showing, I'm going to be converting this to another ingredient. So now step 4 is taking those moles, converting it to grams. So we'll set up our last step using molar mass again to help show that, all right, we're going to follow this step by step. Mass to moles to moles. Molar mass is going to be used to get to our final mass. So we'll take 1 mole of CO2 is equivalent to 44.01 grams of CO2, which we once again get from our periodic table. And then we can show units are canceling, right? So the same color cancels same color. And that gives us our final thing, which is that we're going to make 716 grams of CO2 from this reaction. Now, when you're going through these, how do you figure out how many sig figs? Depending on your professor or your teacher, sig figs may be very crucial, and it's always important when it comes to the lab. So when it comes to the lab, generally it's whatever your measured number is that you started from the beginning. So if you were working with a balance, measuring out how much, let's say how much butane you had or how much of an ingredient you had, you're going to go off your chemical balance from the start or whatever your glassware was that's in the lab. So on a stoichiometry problem, it's always generally whatever the number is that you started with. It's not molar mass that limits you. Now, looking at it all, putting it all together. So the big thing here is how to solve it, what the final conclusions are. The beauty of stoichiometry is that it follows a very set equation every time. Meaning that in order to solve a mass-to-mass stoichiometry equation, you're always doing the same steps. You balance the chemical equation, you start with your mass, convert it to moles using molar mass. You'll then have that reactant, which you'll then go convert it to either another reactant or another product using the mole to mole ratio. From there, you can then convert it to grams using molar mass. And that's how you solve stoichiometry problems. And this is just the beginning. There's more to this. Remember, the goal is always the mole. If you can get to moles, you can convert it to mass, to volume, to gases, liquids, you name it. And we're going to look at future videos to help show that. If you like this video, please consider liking and subscribing. And I hope to see you in the future. This has been Dr. Dan, and I hope this video helped you. And hope you all have a wonderful day. Bye now.